Assalamu alaikum, welcome back. Okay, so we are continuing with our fine-tuning of the universe lecture series. We're here at lecture 4, continuing to talk about initial conditions of the Big Bang. And in our last lecture, we explored the unbelievably fine balance that had to be there between expansion speed and density of matter and energy, so that stars and galaxies could form and anything resembling life as we know it would be possible. And we saw numbers like 1 part in 10 to the 60. So that if things were changed by 1 followed by 60 zeros, 1 part in 1 followed by 60 zeros, a life as we know it would not be possible. And I just wanted to, again, reintroduce you to this conceptual diagram that the universe could not expand too fast because otherwise stars couldn't form, matter would be too sparse. It could not expand too slowly, otherwise it would collapse upon itself. It had to expand just right. And we saw, as promised, that this conceptual diagram really does not do the situation justice. And so let us now put some numbers to this. We've given the numbers in terms of percentages, 1 part in 10 to the 60 and so forth, but just so that you get a feel for the situation in terms of what the actual density is to the level of the best estimates that we have. And by the way, I'm trying to reference everything that I show so that you can go back and take a look for yourself. And so this is from Ned Wright's cosmology tutorial. He's at UCLA. And basically, if you look here at the time since the Big Bang and the so-called scale factor of universal expansion, we see that this green curve, the universe is expanding too fast for life to form. The black curve is the current expansion, which is just right. The red curve is the universe collapses too soon, before our era, before our planet, and so forth. And you see that right now there's a big difference between the curves, but the further back we go in time, we see that the curves approach each other. And so to be able to pick out the black curve where life is possible from the green or the red, let's look at how precise the balance had to be. The density of the early universe at 1 nanosecond after the Big Bang is estimated to be 447 sextillion grams per cubic centimeter. This would be the precise number right here in black. You can see that that number ends in 16, so 447 sextillion, and et cetera, 16 grams per cubic centimeter. And if we add only 0.2 grams to that, so take 447 sextillion and change, and add only 0.2 grams so that it becomes 16.2 instead of 16, we go on the red curve and there's a big crunch, which would have occurred by now. So we would not be here to talk about it or think about it. If we similarly take away 0.2 grams from 447 sextillion grams per cubic centimeter, if we take away 0.2 grams per cubic centimeter, then we have a matter density omega that's too low for our observations, something that would not have allowed stars and planets to form. And so the density of the Big Bang at 1 nanosecond after the explosion was set to an accuracy of better than 1 part in 2,235 sextillion. So you can imagine the fine tuning involved. So if you ever wanted to know what the density of the early universe was, here it is. And even earlier, where the estimates, we are less confident in the estimates, it's set to an accuracy of better than 1 part in 10 to the 59, and we've already seen these figures. But estimates that we're very confident about is 1 part in 2,235 sextillion. So an amazing level of fine-tuning at the origin of the universe, and you see how easily we could have been on the wrong curve where no life would have been possible. And so this density, the right density, puts the universe at an omega value very close to 1, again known as the critical density, where space is so-called flat. Space is not open and space is not closed. It is rather flat. And that's a whole big topic in the geometry of space that we really don't need to get into. But it is this flat space, being very close to flat space, that allows life to form. And all of the measurements that we have are indeed that omega is extraordinarily close to the critical density. So the question becomes, how did this fine-tuning occur, if not by divine design, for example? And so if we want to look at just purely physical mechanisms, well, the theory of inflation has been posited as a way for space to be essentially flat, to be at that critical density where life is possible. And the theory of inflation posits that at the initial explosion, there was an unbelievably rapid expansion of space, known as the period of inflation, that then gave rise to a more gradual expansion of the universe. And the theory of inflation, even though it is, in all the textbooks on cosmology and so on, when you look at it critically, it has now begun to receive some very serious critiques that there are very serious problems with it. Number one, why does inflation start? Number two, how does it end? That's known as the graceful exit problem. Number three, the same force that drives inflation is what is felt to underlie something known as the cosmological constant that we will talk about momentarily. And so it turns out that there are now actually hundreds of different theories or models of inflation. And for inflation to be just right and conquer these various problems, it has to also be as fine-tuned as the things that we're talking about. And so the force that would have produced inflation brings us to the notion of the current cosmological constant. So what is the cosmological constant and why are we talking about it? The reason that we're talking about it is when we said a whole bunch of different things have to be tuned in the Big Bang, the expansion speed, the density of matter, energy, and so forth, it turns out that the cosmological constant also has to be incredibly fine-tuned. So what is this cosmological constant? Well, it is some sort of energy field in the vacuum of space that helps drive the expansion. The cosmological constant has a sort of rich history of its fortunes going up and down. What you're seeing here are Einstein's equations of general relativity. And when it looks here like it's just one equation, but these are so-called tensor equations, nonlinear partial differential equations, 16 of them wrapped up in this tensor notation that relate the curvature of space-time to the energy density in space. And when Einstein initially wrote his equations, discovered his equations, the cosmological constant was absent. And we've already covered all of this in a previous lecture outside of this series, so I don't want to spend too much time on it. But basically, it turns out that when solutions to Einstein's equations were proposed, Friedman's models, Lemaitre's models, and so on, that the universe was not static according to these equations. The universe either had to be expanding or collapsing. And Einstein, as we mentioned, even though he could think very much outside the box, was not able to break out of the scientific prejudice of the last 2 millennia that the universe was eternal and static and unchanging. So how to fight the gravitational collapse that would have occurred in his universe and keep it static? Well, he introduced a fudge factor known as the cosmological constant, given by this Greek letter lambda. And by introducing the cosmological constant, he could keep the universe static as he believed it was. 10 years later, when Edwin Hubble discovered that the universe was indeed expanding, Einstein said that introducing the cosmological constant was his greatest blunder, and if he had just trusted his equations, he could have predicted on purely theoretical grounds the expansion of the universe. So the cosmological constant sort of went away and died for a few decades. Then recently in the 1990s, it was discovered that the universe was expanding at an accelerating rate. We know that it would be expanding from the Big Bang, but we figure the attraction of matter would sort of slow that expansion as the gravitational force of the matter pulled, just like you throw a ball up in the air and the force has it go upward, but it goes upward at an ever decreasing rate because the force of gravity then eventually pulls it back down. It slows its ascent. Or when a bomb explodes, the pieces are going at a very fast rate and then they slow down and so forth. So it turned out that actually the universe is expanding at an accelerating rate. And this, of course, garnered a Nobel Prize in physics for that discovery. Well, what would make it expand? Well, the cosmological constant that Einstein had initially postulated, the so-called vacuum energy of empty space that could drive this accelerating expansion. So if there is indeed this vacuum energy driving an accelerating expansion, how fine-tuned did the cosmological constant have to be so that the universe did not expand too fast to preclude life? And it turns out that, again, an amazing amount of fine-tuning, a required accuracy of at least 1 part in 10 to the 53. And this would be a conservative estimate of the accuracy of the cosmological constant. Now here looms a very large problem that I want to introduce you to, and that is known as the cosmological constant problem. So that's not a very creative or descriptive name, but let me try to flesh it out a little bit. And here's an article from Physics World saying how a new generation of physicists is taking on the cosmological constant problem, trying to tackle it. And this long-standing problem of the cosmological constant, described as, quote, the worst prediction in the history of physics, and by Einstein as his biggest blunder, is being taken on by a new generation of cosmologists. And the article says that the cosmological constant has been a thorn in the side of physicists for decades. So why is that? So simply put, lambda describes the energy density of empty space. And the big issue is, well, where does this energy density come from? We're saying it's empty space. How in the world could empty space have an energy density? Well, it turns out that from quantum field theory, empty space, the vacuum, is not really empty. Things known as virtual particles pop in and pop out according to the laws of quantum mechanics, and they create an energy as these virtual particles annihilate, and we have these quantum fluctuations in the energy of even empty space. It turns out that empty space has an energy density. And when quantum field theory, which has been tested in many ways and is thought to be the crowning jewel of scientific achievement, is used to calculate the energy density of empty space from all of the known types of virtual particles, it turns out that the theoretical value is bigger than the actual cosmological constant by a factor of 10 to the 120 or 10 to the 121. So it is not 10 times bigger than the actual cosmological constant. It's not a million, it's not a billion, it's not a billion, billion. It's a number that is 1 followed by 121 zeros. That's how badly the divergence is between the theoretically predicted cosmological constant and the actual measured cosmological constant. And that is why, again, here's something from University of Chicago Press. What's the problem with the cosmological constant? The cosmological constant problem is widely considered a crisis in contemporary theoretical physics because there is this incredible divergence between the predictions of a theory that we very firmly believe, quantum field theory, and measurements that we also believe are quite accurate. And so how can this be? Well, it turns out that the cosmological constant is actually very complex. It's made up of multiple parts. It's made up of something known as bare lambda and quantum lambda. And the cosmological constant can have parts that are positive and parts that are negative. And so for it to be very, very close to zero, which is the calculation now, Einstein thought it was zero. There was no cosmological constant. Turned out there had to be a cosmological constant, but it is only a very, very small amount bigger than zero. Well, theory predicts that it is 10 to the 120 times bigger than we measure it. And so it turns out that the negative and positive parts of the cosmological constant have to cancel each other out to make it almost zero to better than 1 part in 10 to the 50. And John Leslie says that how this beautiful result is achieved is totally unclear. While we could invent mechanisms to perform the trick, it can seem best to treat such precise cancellation as a question of chance, that is, of what would be quite likely to happen somewhere inside any scientifically gigantic reality. So if there were an infinite number of universes, one of them would have the proper cancellation, or else of divine selection, that you cannot get this lucky without either an infinite number of universes to choose from or divine selection to make the cancellation be such that the different parts of lambda cancel and make it almost zero, which is what would be required. And he goes on to say that it could seem that the cancellation cannot be dictated by a fundamental law. And meaning that it's not like we've probably missed some law of physics that should make it zero. Why? Because the quantum activity in the vacuum involves a whole number of different quantum fields, each of them contributing in a different way to quantum lambda. And so it becomes very difficult that there would be one theory that would reduce everything to zero, because these quantum fields have been detected and tested in a whole variety of different ways. And this problem cannot be explained away by inflation. Maybe we could have explained flat space by inflation, but the lambda cancellation cannot be explained by inflation, because inflation could occur appropriately only if the cancellation was already enormously accurate. That's what I was telling you, that inflation itself would have to be very fine-tuned. And the cosmological constant today is 0 to better than 1 part in 10 to the 120. So it is larger than zero only in the 120th decimal place, but larger than zero, we believe. So here is, again, something from Paul Davies, a very, very well-known astrophysicist, from an article of his called The Anthropic Principle. Again, I just want us to get a visual feel so that it's not all hand-waving. And so he says that one effect of the vacuum energy, which has to be there according to quantum field theory, is to contribute to lambda. And that this dynamical behavior is indistinguishable from the cosmological term in Einstein's gravitational field equations. And so to the ordinary bare lambda, we have to add the quantum field correction. And when we do that, the quantum contributions are some 50 orders of magnitude greater than the maximum limit placed by observation. So bare lambda and quantum lambda are fine-tuned to cancel each other almost exactly to better than 1 part in 10 to the 50. And the problem is that quantum field theory predicts, and scientists have observed, a whole host of different particles. We may be familiar with, protons, neutrons, electrons, but protons are made of quarks, and it turns out there are multiple generations of quarks, and electrons have cousins like muons and tau particles. And each of these scalar particles makes its own contribution to quantum lambda. So you would have to be fine-tuning the contributions of a whole host of particles. And so he gives the equation for how the electroweak force contributes to quantum lambda. And I just wanted you to know that these equations exist, that this is not just somebody sitting back in an armchair and kind of philosophizing. This is cold, hard math. And so the contributions of the electroweak force are on the order of 10 to the minus 2 per meter squared. But when we add bare lambda to quantum lambda, this 10 to the minus 2, which is like 0.01, has to become 0.0000000 10 to the minus 53 zeros at least. And things that go into allowing this cancellation to occur are the universal gravitational constant that we've seen before in Newton's equations. And this is the coupling constant for the weak force. In future lectures, inshallah, we will be talking about the different forces of nature and how precisely they have to be fine-tuned. One of the 4 forces of nature is known as the weak force. It is, for example, important in radioactive decay. And forces are measured or expressed in terms of strength by so-called coupling constants. And this is the coupling constant of the weak force. And so it turns out that if the universal constant of gravitation, or the universal constant, the coupling constant of the weak force, differed from their actual values by even 1 part in 10 to the 50, the precise balance against bare lambda would be upset. Because you see that one portion of quantum lambda here, the universal gravitational constant and the weak coupling constant, both go into determining its strength. And if these, one or the other, differed by even 1 part in 10 to the 50, this force would change. And the cancellation, when you add bare lambda to quantum lambda, would be thrown off, and it would upset the structure of the universe. The universe would be drastically altered. And so this is the electroweak contributions. When we add in the strong force to the electroweak unification of Weinberg and Salam, which won them the Nobel Prize for unifying the weak nuclear force with electromagnetism. Now, if we try to bring in the strong nuclear force, this is grand unified theories, GUTs. This is still being worked out, but if we take a look at equations that incorporate the strong force as well, the balancing act is still more astonishing. The fine tuning has to be at a delicacy of 1 part in 10 to the 100. And so, what are we trying to say here? We're trying to say that this is part of the initial conditions which went into the Big Bang, and we saw unbelievably fine tuning between matter density and expansion speed, fine tuning in the cosmological constant, and we're seeing that this fine tuning of the cosmological constant depends on amazing fine tuning of a variety of the constants of nature. So this is where initial conditions cross over and meld and combine with constants of nature to produce fine tuning. And so we see that the cosmological constant also has to be fine tuned to an unbelievable degree to allow this universe to be life-bearing. And we return again to John Leslie's comment that this fine tuning, given the number of different factors that go in and have to cancel precisely, either you have to say it's a question of chance, which would require a sufficiently gigantic reality, meaning here the multiverse with an infinite number of universes, and we were lucky enough to hit on the one that allows life, or divine selection. There's no other way, to beat these sorts of odds or to come out successful when this sort of fine tuning is required. So let me stop here because this was a lot, but we will keep going in the next lecture, inshallah, showing that there are yet more amazing initial condition requirements on the Big Bang that would have needed to be there to make anything resembling the universe that we observe and anything resembling life possible. And just to foreshadow, we're really mostly here talking about initial conditions. We've begun to touch on universal constants. And in future lectures, inshallah, we will see that the fine tuning extends to the masses of the fundamental particles, to the strengths of the fundamental forces that govern the interaction of these particles. And so it is like a whole bunch of different dials had to be set with an unbelievable amount of accuracy. It's not just one thing or two things, but it is an entire structure of different dials governing all of the different initial conditions, governing all of the masses of the fundamental particles, governing all of the strengths of the fundamental forces that interact between those particles and so forth. And if any one of those dials had been misset, life as we know it could not exist. And these are all entirely unrelated. They come from different branches of physics, from different bits and pieces of physical laws. It's not like saying we have a family that has 4 people and let's say that's a miracle that there are 4 people and that they have 8 arms then they have 40 fingers, but all of those are related. If you set the first miracle that the family has 4 people, they're going to have 8 arms, and on those arms there are going to be 40 fingers. This is entirely different. Each bit and piece of fine-tuning is separate from the rest, and they all have to fall into place just so. And right now, we are at the beginning, looking at the different parts of the initial conditions of the Big Bang that had to occur. And then later on, inshallah, we will look at issues of fundamental forces, masses of fundamental particles, the constants of nature, and so forth. So once again, I hope that I have whet your appetite to continue with me. Take care. Assalamu alaikum and God bless.